In this lecture, we will study about magnetic boundary conditions. So we have already, as a small portion, we have studied boundary conditions for both electric and magnetic field. But that time I didn't go to the derivation and numerical problem. So in this class, we will see how we find out. So you already know boundary condition means there will be two regions and there will be a tangential component and normal component. So how we derive that, and we will do a numerical problem also based on that. So when it comes to magnetic boundary conditions, we have two regions, region 1 and region 2, and they are two different mediums, that is of mu1 and mu2, and we will consider the normal component. So the normal component will be, so we have a magnetic field B2, moving from region 2. So at region 2, I will call it B2, and at region 1, I will call it B1. So it is moving from B2 to B1, and this is the normal. So B2 will be having a normal component as well as a tangential component. So normal component means it will be acting perpendicular. So this is B2n, normal component of B2. So it is making an angle of theta 2 with B2. And B1n is the normal component of B1, which is making an angle of theta 1 with the magnetic field B1. So this much thing is understood. Now we will consider a cylindrical surface of surface area delta S. So we need to derive it. No? So we will consider a cylindrical surface. So you know that the magnetic field, the same magnetic field B2 is entering here also. So you know that it will be B1, it will have B1n as the normal component, and then it will be having B2n. So B2 and B1 will be having their respective normal components, and delta H will be the height. Then by using Gauss law of magnetostatics, Gauss law of magnetostatics, we can write integral B dot ds is equal to 0, and we will consider delta H approximately equal to 0, delta H tending to 0. Then we can write B1n into delta S. So B1n into delta S minus B2n into delta S is equal to 0. So integral B dot d. So B dot ds is the flux. So flux coming out. So B1n into delta S minus B2n into delta S is equal to 0, which makes it, the derivation is very simple only, but still you should draw all these diagrams and write if it comes for a 5 to 8 mark question, which makes it B1n is equal to B2n. So the normal components of 1 and 2, and also you know that mu1 h1n is equal to mu2 into h2n, which makes it, these are the two equations we have. B1n is equal to B2n, and mu1 h1n is equal to mu2 into h2n. So these two equations we have realized. So that is all about normal component. Now, when it comes to the tangential component, so so we have this figure here. We consider a rectangular shape here. So when you consider a rectangular shape, so you know normal component is acting like up or downward. Then the tangential component will be like, this will be H1 tangential and this will be H2 tangential, and let delta W be the width of the rectangular path, and let delta H be the height, which will be approximating to 0, like in the previous case, like in the case of a normal conductor. So now we will see, I'll draw the figure again to make it more clear. So this is B1, this is B2. So you know that if this is B1, then this will be B1 tangential and this will be B2 tangential. So B1, I'll use another color to make it more clear. So this will be B1 tangential and this will be B2 tangential. Then we can say that, so this is our rectangular surface. Rectangular surface A, B, CD and let the width be delta W, and you have the height delta H. So I am again marking it B1T tangential and B2T. No, B already we have marked, right? So we will mark it in terms of H. B is equal to mu into H. So we will mark it in terms of H. So it will be H1T and this will be H2T. So for solving normal condition, normal component, we went with Gauss law of magnetostatics, and in case of a tangential component, we go with Ampere circuit's law. So these two things you should mention. Okay, by Ampere circuit law. So the one who is checking the paper will be seeing whether you have mentioned Gauss law for normal component and Ampere circuit's law for tangential component. If that two things are mentioned, means then the rest of the things you can write. So without mentioning the equations and all, if you write something here and there and make it and show it like it is equal, then you will not get marked. You should write exactly what is the concept. So what is Ampere circuit's law? Integral H dot dl is equal to I enclosed. Then we can write from the figure H1T into delta W minus H2T into delta W is equal to a constant K into delta W. That K is the surface current density. K is the surface current density and delta W is the width. So why we are making delta H very small? Because that is the interface that we are considering. So that time we are considering just a boundary. So boundary will not be a big surface. We are considering, we are taking a surface for our understanding only. So delta H is taken very small because that's just a boundary. So what happens above the boundary and below the boundary, that is mu1 and mu2. That's our focus. So from here we can write H1T minus H2T is equal to K. Then bringing in the mu factor means B1T divided by mu1 is minus B2T divided by mu2 is equal to K. So we have reached here. Then we can write when we consider, so actually only this much is required, B1T. So if in some cases, if the boundary is free of current, if boundary is free of current, that means surface current density is not there, that is K equal to 0, then the equation will be H1T minus H2T is equal to 0, the tangential component. So T means tan component. I'm not writing like tan, so don't be confused. So it is a tan component itself. Okay. So then how we can write? We can write it like, therefore H tan 1 will be equal to H tan 2. Also B1 tan 1 divided by mu1 minus B2 tan 2 divided by mu2 is equal to 0. Therefore, B1 tan 1 divided by B2 tan 2 is equal to mu1 by mu2. So this is the equation that we studied that class, and that can again be equal to mu r1 depending upon the medium. And also one more equation we can derive. So if they are asking you the angle theta, in some questions they will ask you angle theta. So this is B1, this is B2, this is theta 1 and this is theta 2. Then how we will write? B1 tangential component, how we will write? Tangential means along this path, right? I will show with red ink. So this understanding is very much required. So tangential component means like this, right? Should be like this. So considering where we have marked the theta, this will be in the component. Considering where we have marked theta 1, this in the component, sine component, cos component, the red line. Sine component. So that understanding is very much required. So we can write B1 sine theta 1 by mu1 is equal to b2 sine theta 2 divided by mu2. That is the tangential component. And when it comes to the, I'm writing here. Okay, I'll write here because when I give you the notes, it will be confusing. So on the normal component, how it will come? It will be b1 cos theta 1 because I will use another ink. This was the normal component, right? So that will be the cos component. So normal component will be b1 cos theta 1 is equal to b2 cos theta 2. So from this one equation also we can get tan theta 1 divided by tan theta 2 is equal to mu1 by mu2. So if in some question they have given you, they are asking you to find theta and they have given the mu for both the sides, then easily you can find it out. Then one more question we will do. Okay, before that, if you have any doubts, let me see. So here we are given a question which says, it is actually a boundary condition based question. The magnetic materials are separated by a surface Z is equal to 0, having mu r1 is equal to 4 and mu r2 is equal to 7. So the value of mu for both the regions are given. Region 1 is at Z greater than 0 and region 2 is at Z less than 0. The surface density Ks is given as 60 AX ampere per meter at the boundary, and we have given the field B1 and we need to find B2. So first of all, we'll draw the figure. The figure will be, so we'll consider a boundary here. So this is Z equal to 0. So Z greater than 0 will be here and Z less than 0 will be here. So we will consider this as region 1 and this will be region 2. Okay, so we have our B2 entering and this is B1 and you know all the concepts related to here, that is theta 1, theta 2. So everything you know. So you know what will be the normal component, how to mark and all you know. But here we need to analyze this problem. So moving ahead, we need to find the normal component. We'll go with our standard equations. So we have boundary is at Z equal to 0. That means B1n is equal to minus 3AZ, right? C1. So B1 is given as AX minus 2AY minus 3AZ. So in the boundary in the boundary will be, okay, in the normal component upward and upward and downward B1n downward upward and this will be B2n and this particular figure direction. What is this normal direction? Z direction നമ്മുടെ XYZ plane എടുത്തു കഴിഞ്ഞാൽ this upward B1n direction is the Z direction itself. Is it clear? That point clear ആണോ? Hello? Yes. So the Z coordinate of B1n, B1 will be the normal component. So B1n is equal to minus 3AZ. So that understanding will make you do this problem. Okay, from the base, equation you should understand which is the normal component, then only you can move ahead. So from that you understood that B1n is minus 3AZ because they have given Z is equal to 0 is the boundary, and you know normal component will be like this only. So that is B1n. So B1n is actually, so this is Z, this is Y, and this is X. So this is the Z component. So normal component is the Z component itself. So B1n is minus 3AZ. So if you have the vector B1 and if you have the normal component, then you can find the tangential component, which is the vector B1 minus the normal component, which makes it AX minus 2AY. So വളരെ simple ആയിട്ട് പറഞ്ഞു കഴിഞ്ഞാൽ Z normal component Z component ആയി കഴിഞ്ഞാൽ ബാക്കിയുള്ള രണ്ട് component tangential ആയിരിക്കും. So അതിന്റെ mathematical understanding ആണ് ഇത്, AX minus 2AY. Now we will apply boundary conditions, which says boundary condition B2n in B1n normal components are same. So B2n equal to B1n and 3a is set. So in this particular question, we are asked to find B2. So B2 will be having x, y, and z coordinates. So in that, we have already found out very easily what is the z coordinate of B2. So now we need to find the x and y coordinates. So x and y coordinates for B1 is actually tangential only. So similarly, the B2 components will also be, x and y components will also be tangential. So we will apply the boundary conditions for tangential. We will apply the tangential boundary conditions. Okay, now we will go for the tangential component by applying tangential boundary conditions. By applying the tangential boundary conditions, what do you get? H1t minus H2t is equal to Ks. So you already derived it, and you must have seen the question. Ks is already given. V1t minus U2, U1 by V2t minus U2 is equal to K into S. Okay, so how we will proceed with that? So you can write, so H1t minus H2t and the equal to Ks on the. Then what does that mean? This can be also be written as H1t minus H2t cross product with A21, because A21 is a unit vector, is equal to Ks. So that also doesn't change the meaning. So this we can also write B1 by mu1 minus B2 by mu2 cross product with unit vector is equal to Ks. Unit vector is a normal vector. So A cross B is AB sine theta. So it will be AB sine 90. So it will be AB itself. So A itself. Here our B is the unit vector, AN. So that is not making any difference for us, right? Tangential component means it's not making any difference. So from that we can write, and Ks is also given. So we can write, it's a bit complicated, so listen carefully. So Ks is equal to B1 we will write Ax minus, so actually not tangential, B1 by mu1 is equal by B2 by, like that only, because we have taken a cross with AN, right? Yeah, this step is correct. When it comes with cross product, then no need of tangential component because it is taking AN. So Ax minus 2Ay minus 3Az divided by mu R1. So mu R1 will be 4 into mu naught, because what we have given is 4, and mu R2 is equal to 7 into mu naught. So minus B2Ax. We can B2Ax B2 AY1, B2XAX and B2YAY1 B2X is already on, so still, but we'll go step by step. A is by mu R2, that is equal to, and then Ks is given. Ks is given as 60Ax. So you should solve this equation. Either solve and equate the x component equal to 60. I will do some more steps. So just I'm giving you what to be done. Then 7Ax minus, so I am taking the denominator and going ahead. I prefer you to do it on your own rather than copying my step, but I will solve it here and you do it on your own, then check my steps. So B2y AY minus 4B2Z AZ, and it was the normal component, right? Cross product with the normal component. In this particular condition, the normal component is what? Already mentioned. The normal component is the Z component itself is equal to 60 into that 7 and 4 will multiply. You know how to take LCM, okay? 28 into mu naught. So it will be minus AX and AY components. So minus 14 into 4B2Y into AX plus minus 7 plus 4B2AX AY is equal to 1680 mu naught AX. Okay, so this is 4B2X actually. Okay, 4B2X actually. From this, even the year B2X. Okay, then we can write. Then you equate this with this value. The X components normally equate here. You will get B2X is equal to 7 by 4, which is equal to 1.75. And if you equate the Y components, you will get, I mean, this is the Y component you are equating. And if you equate the X component, you will get 14 minus 4 B2Y is equal to 1680 into mu naught. So B2Y, we get it as minus 3.5 AY, and this is AX. So B2 we can together, you can write it as 1.75 AX minus 3.5 AY minus 3 AZ. So do this on your own and tell me if you're not getting this final answer. So B2 you can find it like this, and if you're asked to find the angle theta, then go for this equation, tan theta 1 by tan theta 2 is equal to mu 1 by mu 2. So this way also you can find it out.